Okay, so I have here, let's start with this, and I have collected a couple of topics. They are short, let's say, short stories of a few slides, and I have several of them. I don't want to talk about all of them, it probably cost too much time, but I pulled out the 3 topics, and I show them here as a question, as a kind of a quiz, and maybe actually this is cool, and you're supposed to learn something, and maybe from the stuff that you learned, maybe you can answer the question already, or can guess it. So these are 3 topics I have chosen because they're interesting. Here, for example, that's a long story that I had many discussions with Fritz since my PhD thesis 20 years ago. Which tip is better, a sharp tip or a blunt tip? A sharp tip makes more field enhancement, a blunt tip less. Which tip is better? And we could have many days and weeks of discussions we had, actually. I can give you the solution, but maybe I give you some seconds to think about it. Okay, so that's the first question that I have. Then the other thing is, here we see the topography gold on silicon, and then sometimes around such edges we see kind of a fringe close to an edge. And just recently I saw a paper in nanophotonics, not so old, few weeks. I think it's a nanospec, an airspec publication. This is they saw similar stuff on doped silicon, and they say this is a polariton. So is this fringe that eventually decays here a little bit? Is that a polariton? Think about it. And the other thing is, and that I saw lately quite often in the lab, and the solution is quite simple. But if you don't know it, it's maybe tricky. So here we have a topography image. This is, I think, Eugene actually did the experiment. What was that? That was some dirt particles on top of silicon. That's the topography image, and that's the optical amplitude image. And it happens quite often that you see this kind of jumps here in the amplitude signal. They also appear in the phase signal. What's that? Where it's coming from, and how can you get rid of this? So 3 questions. If some of you has any idea, knows about that, I don't know. So have we thought about it? Who has seen this kind of effect? Particularly if you work with the sticky samples, polymers, you may see that. Who has seen this already, or who knows what this could be? Yeah, I don't know. Maybe we use the microphone.
Just a question. You mentioned it's topography, but it's written M1 amplitude.
Sorry, this is incorrect. This is a topography. It's a topography image.
Okay.
If you have a closer look, you actually see this kind of strange, noisy features in there too. But here in the optical signal, you see them better. So there was somebody knew about it. Yeah. There's some. No, it's silicon. Huh? I think it's silicon, and it's maybe a sticky sample. Yeah. So okay, but why is a sticky sample producing that crazy stuff there? It goes in the right direction.
Sticks to the tip.
Yeah. Well, maybe. Yes, I show you later on. Yes. Okay. So a mechanical phase, right? Their phase jumps too. Yes.
Maybe. Oh, sorry.
Yeah. Yeah.
So I've seen this before, and usually surface charge can cause this. So if we ground the sample in a better way, I already solved some problems.
Okay. Yeah. Right, these things appear in similar effects. It's not the case here, but you're right. Charging may produce that too. It's actually related. I hope later on, then, on the help of our AFM experts, I will ask him then, because I cannot probably explain it so well. Okay, so we have, you see that? Somebody else who wants to? Wow, it's amazing.
Change
what?
of
Yeah.
Change of tip radius because
no. Yeah, next one.
Bad scanning parameters. Maybe the tip is flowing over the dirt too fast.
Yeah, becoming in the right direction. Scan parameter is, if you change the scan parameter, we can fix the problem.
Yeah, because the edges of these spheres are not so sharp.
Yeah.
So maybe the scan parameters are wrong.
Okay, so last one, then we need to move on. Yeah. Yeah, it's also a phase.
If it's in the phase, then it might be switching between attractive, repulsive regime or vice versa.
Bingo.
I think.
Here's the winner. So I will explain in a second in more detail. So, okay, good. So we solved this very good. We have 1 out of 3 correct answers already. So now, polariton, which one tip is better? Any point to this? Yeah? Here? Yes?
We have sharp tip, so we can get much of the field emission from the tip, and that can basically put more noise into the signal.
Mm-hmm. So blunt tip is better?
Yeah.
Okay. Who votes for the blunt tip?
I think it depends on what you want to scan.
Also a very good point. Good. So let's assume we scan our standard samples, which are not, okay, let's say we scan larger areas, right? Like transistors or big patches of membranes. But the answer is pretty okay, right? It's very good.
My personal choice is the sharp tip.
Okay.
Because I think sometimes if you have a very big tip, you can induce some other kind of effects
Yes.
in the tip due to the geometry.
Yes.
So that's
Okay.
Mechanical speaking, I would go for the sharp because then you
Okay.
control the
Well,
distance from the sample.
Okay, let me refine this. Maybe it's a little bit unspecific in terms, of course, near-field signals. So which gives you the better near-field signals, let's say better signal to noise. So I think we all agree, I don't make this too a quiz, sharper tips give you more field enhancement, correct? I think the Thirst people particularly know that. You want to have the sharpest possible tip, because the sharper the tip, this is actually what I said. The sharper the tip, the more field concentration, the more field you have. And the signal, one knows a little bit roughly, scales with the force power of the field enhancement, at least in terse, right? So sharper tip should be better. That's at least what I discussed a lot with Fritz. And so let's vote for it. Let's assume you want to scan, let's say, well, actually I showed an example. Take an HBN flake, close to just dielectric map of an HBN flake that is a few micrometer large, and it's on silicon, and I would like to see this flake with a very bright, good contrast. Which tip is better, this one or this one? The blunt or the sharp one? So who is for the sharp one? Fritz, of course. And the blunt one? Okay, good, the majority. Very good. Maybe you guys read the paper. Okay, now here, at this edge here, you all know, I mean, we've seen it already quite a bit. Typically, you see a lot of fringes, and we know that if you have a polariton that is quite damped, like on bismuth selenide, I don't know who showed Martin showed yesterday some images from us, then very often you see only one fringe or a fraction of a fringe. So it's on the scale. It could be a polariton, right? Is this one here or not? Or who has seen this already at close to topography edges? Has somebody saw this already? Yeah? Yeah? Vladimir? Again?
It's always fringes near H.
Right.
You just ignore them.
Okay.
Don't call them.
Okay. Good point. There was another? You just ignore them. Okay, good. Very good. Okay, so yeah, we solved nearly all the questions. So then let's explain me a little bit. I want to start with this one. It's called Chapter's Influence of AFM Mechanics.
Rainer, can you go back to the previous slide? I have one question to your two tips.
Yeah, this one, yeah.
Yeah, the fact that your upper tip is not radially symmetric, isn't that a problem?
I don't know. Good question. It's something that one should and could explore. So these are
at
two.
the sharp edges, you will also get very strong near-field enhancement.
No, it's a good point. And indeed, there are certain type of tips. If you illuminate very sharp edges, sometimes they don't work very well. I don't know. I really cannot tell you this, but it's definitely worth to look into that. And also, Fritz showed some images. These guys are kind of antennas, and they're long, and they may have emission lobes. There's something we, many years ago, tried to elaborate a bit, but not very successful. But in principle, these are antennas. They may have lobes. And if you think, for example, of these stealth fighters, right? These invisible planes, right? I don't know what happens here. If you have a sharp edge and you illuminate it, you may not couple very well to the antenna. I don't know. It's really, as I said, one of the idea of this workshop is also to make very clear we know a little bit of s-SNOM, but there's a huge parameter space and knowledge space to be explored. I really don't know whether here the geometry plays a role. Probably, but I cannot tell you in which sense, okay?
Okay.
Yeah. All right, so let's start to the first topic, which is called influence of AFM mechanics. That was actually related to Tobias' answer. So here now you see the full set of images. I used here a set point of 72%, not me, Oshania, who's sitting here, did this experiment, I think, if I remember correct. And so we have that's the topography, that's the mechanical phase image, that's the optical amplitude, third harmonic, and that's the optical phase image, okay? So now we see here these jumps here that occur all over, and they are particularly seen also here in the optical phase, and this is what I always recommend. If you see that, look at the mechanical phase, and in the mechanical phase you see these jumps as well. So, and you see even here, one would need to zoom in, you see there are jumps in the topography, but there are no jumps in the topography. This is super flat silicon. So there are jumps in the topography. What is going on here? So, and here now I may need to help, need the help of Lucas a little bit. So it's always very, very good. Not many people are doing it nowadays. When I started with s-SNOM and AFM, people looked much more at the so-called approach curves. So what we do is, we have here the tapping amplitude of 70 nanometer. We approach the tip, and that's the mechanical oscillation. And we approach this now. Now the tip comes into contact. So now the tip apex, once hitting down, is touching, right? And now if we approach the sample further, what happens is that the amplitude gets damped because the feedback is switched off, right? So that means we have a linear decrease on the amplitude, which is actually a way of measuring the amplitude, because from this slope here, you can measure the tapping amplitude instead of using the nanoGUNE whatever button, which I don't like at all because it's just an estimate. So from this slope, you actually can measure the tapping amplitude. So in an ideal case, it goes down linearly. But what you see now here is that at this circle that I mark here, there's a jump. And also, we approach the sample, suddenly the amplitude becomes larger. So what I come closer with the sample, and the amplitude becomes larger. So how can that go? And if you look at the mechanical phase, which Lucas was mentioning, what we see is that there's a huge phase jump. So first, if you come into contact, first the phase becomes negative, and then it jumps, and suddenly it's on the positive side, relative to the free oscillating phase, okay? And that's the optical signal here. So we see this typical increase here until here, and that's where we typically show it. But if you now go further down, what happens is the amplitude goes down, the modulation amplitude goes down, and then the signal behaves somehow strangely. And this behavior is not very reliable and predictable. You can see here any type of behavior. But then the interesting thing, suddenly the near-field signal jumps quite significantly, can jump up to a factor of 2. And the optical phase jumps too. So what's going on here? So this jump here has to do with the mechanical interaction between tip and sample. And Lucas mentioned there are attractive forces and there are repulsive forces. And here we are in tapping mode. And here you may need to help me a little bit. So once we come closer, once this jump appears, as far as I understood that, is that we go from dominantly attractive interaction to dominantly repulsive interaction. And in this case, what happens is that because of the attraction, the tip returning point is a little bit above the sample, 1 or 2 nanometers. But once we come into repulsion, then the tip hits the surface, and it goes a little bit closer to the surface, and that is 1 or 2 nanometers. So the tip comes closer to the sample surface. Is that more or less correct? Yeah, that's the kind. Yeah, exactly. So the tapping amplitude, and that's the reason why the tapping amplitude gets a bit larger. But there are many things that happen. For example, now we have this repulsive interaction, and that's like a really hitting. And what happens is that the sinusoidal motion could become unharmonic. So we could generate a lot of higher cantilever harmonics, cantilever modes, and that could lead to, let's say, modulation of the background. So, but that could be the reason for this jump here.
But that depends on the mechanic of the cantilever and the status of the tip.
Yes, yeah.
It's not a general rule.
No.
It's very specific.
No, this is
of the moment that you are doing that.
Right.
Because if it's soft or stiff,
yes.
it depends, and if it's
yeah.
more roundish or more,
Yeah.
sharp, it also depends.
But where this happens is actually depending on many parameters, but typically it happens, and particularly with the clean, sharp AFM tips, this happens. With the platinum tips that we use, this is a particularly nice example, and we worked hard to get it so, let's say, textbook-like done. But in the end, it's a phenomena that is studied a lot in AFM, and with very sharp pointed tips, this is a phenomena that I would say regularly occurs. Right? And so where this happens, at which set point, depends on the tip radius, on the cantilever type, and so on, okay? So the thing is that there are these jumps, and now the set point is here. We imaged here, and that's also called the bistable region. Depending on the interaction, whether you are now here or here, this jump may move up and down. So if I'm imaging here, I jump between these two positions, being repulsive and attractive, and then the signal, so the topography jumps, the mechanical phase jumps, and this you see in these jumps here. Then the optical signal jumps here. Whether this is now real near-field effect or not, I don't know. And the optical phase jumps, okay? So this is a situation, and this is not something that occurs rarely. That happens quite often. And many people don't notice it so much, particularly if you have, let's say, not such a good signal to noise because you work with a source that has a lot of noise, then you may not see it even. So that's due to interaction, and it's really quite unexplored what is going on here. Is it an artifact or is it a real effect? Do we get more near-field signal because the tip comes closer to the sample? Could be. Then we could exploit that. That could be a positive effect because we suddenly get much more signal. That could increase the signal to noise. Or it's just a modulation of background. I don't know, to be explored. So here I just want to show the solution is rather simple. In this case, you change the parameters that was mentioned already. And you can change different parameters. You could change the tapping amplitude, the set point, the frequency. Sometimes you need to play around a little bit, and that's it. And here in this case, we just go up to 83%, and then most of these jumps are gone. They're still partially here, because the sample, as I said, it was a little bit dirty, sticky sample. You see here in this marked region, pretty clean. So it's the only thing. You change the set point by 10%, and you're all done, okay? Sometimes this does not help, and then you may need to change the tapping amplitude or whatever. So,
if I may comment, but
yeah, sure.
You can also change the continuous stiffness because NSPEC provide the 75 kilohertz or the 300. If you go to 300, maybe you wash out.
No, there are many parameters you can change. Just,
and also there is something else that many times I try to ask. NSPEC is to give control on the amplitude once you are in contact.
Oh yeah.
Instead of the set point, because that will allow you to set the energy.
Yes, I would. Actually, I'm pushing for that since always, that we have more flexibility to change parameters while scanning. The aspect is very restrictive here because, of course, you can make a lot of nonsense. If you change the wrong parameters during scanning, you crash the tip and then you start from scratch, or you start doing even worse stuff. But let's say for a little bit experienced user, it's really helpful. Like in the old version of the microscope, one could control the things in parallel. You could even change the driving force while scanning. This is now completely disabled. And that gives you a lot of access to fine-tune this mechanical tip-sample interaction, which is really important. And it particularly for a little bit complicated sample, this is very helpful.
Because depending on the radius of the tip, you may change the set point, maybe not enough.
Yeah.
So.
Yeah, absolutely right.
Ryan?
Yeah. Okay, you have a mic.
You can also change feedback, and you can do it while in contact.
Yes, the feedback will not change here much because that's feedback independent. Here the feedback is switched off, right?
You mean so if it's PID, you can change your feedback loop.
If you do frequency control, but the s-SNOM is not doing that. So here the feedback is switched off. So with the feedback you will not change here much. You will not improve the situation much, I guess. I'm pretty sure you will not change it.
You clamp your cage up, you basically physically approach your tip to the surface. So you don't want to have the PID on because then it's getting complicated. Even more complicated.
Okay. Yeah. No, I think feedback I don't think will help you much.
Sometimes it's helpful just to move the sample a little bit lower, and then you retune the mechanical frequency of the tip, and then it's more stable.
It would be much better to control the amplitude so that you know what you are doing instead of trying. That's one point.
Okay. Okay, I think we need to move on because time is really running, but okay. So that's it, what I wanted to show regarding this. There's not so much to say. Then some influence of sample edges. So what happens if you go around edges? This also goes back to my time with Fritz. We called this edge darkening artifact. So the thing is, if you have sharp edges, what happens very often, you see these dark fringes around here. And in a very, that is from a paper actually from this one here, it's a very intuitive picture. So how we see that or saw that at this moment was if we have the tip close to the silicon here, the tip is very close, we have a lot of near-field interaction, we get a lot of signal. The same is true on gold, and as gold is has a higher refractive index, we get more signal. But now at the edge, the tip is roundish, there's a certain diameter, and it lifts up, okay? And then it probes a lot of air, which has a refractive index of 1 or dielectric function of 1, and then in the end the signal is reduced. So this is how we explained these dark fringes here, but roughly like this, right? And then, yeah, sure.
So Rainer, in that case, the fringe is always comparable to the size of the tip?
Yeah, we will see this then later on with the blunt tip example. So, but here we see this only a dark fringe, right? No, not necessarily, because it's a near-field effect, and the near-field is not so much depending on the direction. So you also see it here, right? I mean, it's pretty symmetric. It's really kind of going all around, right? This is something that is very. It's not big science what I'm showing here. It's just let's call it tips and tricks and phenomena, but without really being very well elaborated. So then, what one sees very often, or sometimes, is that there's not only a dark, here you see the edges here, and then the signal drops here. That would be this dark fringe. And then there's very often a bright spike next to the edge here. And here you see it in the image, and the beamer you don't see it so well. You see here this dark fringe, and then you see a bright fringe here. And here in this paper, they mark here this with stars, and they say this is a polariton, and these are further polariton fringes. I don't know, maybe the author is even in the room here, I hope not. I don't think these are polaritons, to frankly speaking. I think this is just an edge fringe that, who was it, Vladimir, you said, just ignore that, right? You should ignore it. And yeah, so one sees that, ignore it, that's the thing, but I can give you a physical explanation for this. This is a paper from Victoria Babicheva and Johannes Abate, I think was involved there. And what they did a numerical simulation, and they calculate numerically, scanning a tip along here a layer on a substrate, and they get such a line profile. They see this kind of, at the edge, the signal drops down, and then we see this spike here, this sharp fringe that is on the substrate, close to the layer. And so they had obviously here two materials that are pretty similar in the dielectric function. So what's going on here, and that's very nice, they show here field distributions at these different positions. So as we shown before, just intuitively, the tip is very close here. We have some interaction here between the tip apex and the surface. The same is true once we are here on top, right? So the tip is nicely interacting with the flat sample surface. But then, and that's how they interpret it here, once we are here at the edge, right? The tip is far away from the substrate, and then the interaction altogether is reduced, and one can see it here. They are not these really bright spots, these bright spots that one have here, right? So the near field altogether is a little bit lower, and that gives rise to the drop in the signal. But now, there's this situation where this peak appears, and what they calculated here is, I think, really the scattering from the tip. But in the near field, we see that there is interaction now between the tip apex and the substrate, one hotspot, or one strong interaction, and there's another one between the tip shaft and this very sharp edge here. And so they say here the interaction is strongly enhanced because of tip-substrate coupling plus tip edge, tip shaft edge coupling, okay?
But,
so I think this also requires further systematic modeling, but I think it fits quite well.
Where is the illumination coming from in this case?
I don't know.
They may be a bit dependent on the illumination, right? Because
illumination could play a role. Also, I should here cite again Vladimir. He said there is no reflection of whatever. We are here in a diffraction limited situation, right? Particularly in infrared. Whether the light comes now from here or here, are there shadowing effects and so on? This discussion sometimes comes up. I don't know. Okay, so to be explored.
Just to add to this, actually, what you have at the edge, it's clear we have an enhanced or more sources for, let's say, near-field coupling. That's one thing. But at the same time, we have also that all the other forces of your tip going up and down are also coupling to the edge, right? So it's not only the front end that at this moment makes an interaction attractive or repulsive, but it's also the edge, which means your feedback goes crazy and says, oh, I have to pull back. I have much more force feeling at the moment because I'm going bang to the edge. So this signal, this peak, is then convoluted by the mechanical phase, right? So phase and phase and phase. So keep scratching your head.
Good. So conclusion. Better ignore the fringe than interpreting it as whatever, okay? But to be explored, that's an open topic. What is the influence of topography? I would even have, depending on how much time I have, I would have even other really interesting examples on how topography can dramatically affect near-field optical contrast. Okay, now, influence of tip radius, so that we had already this quiz. Now I show you here that's calculation. Actually, it was hard to find here some of this systematic calculation literature. This is from unpublished data from Stefan Mastel calculated this during his master thesis. So this is in infrared. I think this is COMSOL calculation where we calculate here. That's the field distribution along this tip here for tips of different tip radii, right? 2 nanometer up to 20 nanometer. And what you see here is that the sharper the tip, the more field enhancement you get here, right? So this is not normalized, this is just volt per meter. I don't know how much the field enhancement is here in terms of field relative to the incident field, but it clearly shoots up. This is what is expected. Sharper tips are better. And I would say, clearly, if you are interested in imaging a single molecule, then for sure it's better to focus everything on a single molecule with a 2 nanometer radius tip rather than with a broad tip, okay? But we do that in TERS, and that's why the TERS people probably like very sharp tips. But we are typically not looking at molecules. We are typically looking at larger features like flakes and so on. And so that's the experiment what we did. So actually, you can buy, this is a standard tip, and this is Team Nanotech tip. So these are silicon tips that are coated with I think it's gold coating, I'm not 100% sure. And you get them from 250 to 750 nanometer radius, and they work excellently. They're really, really nice and stable. And actually, we use them for terahertz imaging, because in the terahertz, and these are terahertz images that I show you now. So here we have a 25 nanometer tip, and here we have a 500 nanometer radius tip. It's huge. And that's an HBN flake done at 118 micrometer wavelengths. That's the scale bar here. Look at this, 2 micrometer. So here, that's HBN, that's graphene, and that's the silicon oxide substrate. So the graphene, we see here very nicely. It's bright because it's quite conductive in the terahertz. So it's like a metallic layer. And then we barely see a contrast here between the oxide and the HBN. And you may see, okay, it's slightly darker, but it's hard to see, okay? And then look at we have the dark fringe. That's the edge darkening artifact. It's rather narrow. Now we use this blunt tip, otherwise we do everything the same. And look at this increase of signal to noise. It's amazing. I mean, we were really pretty amazed by that. Of course, you see that the fringe gets broader here, right? So the resolution goes down. But still, I mean, this is a 500 nanometer tip. That means the diameter is 1 micrometer. And the resolution is not that much worse compared to the signal to noise you gain, yeah?
Is it anything to do with the fact that you're using 118 micrometer wavelength?
Yeah, also good point. Yep. Okay, yeah, I can't.
It's like it doesn't exist, that tip, right? It's so small. It's 25 nanometer with respect to something that is It's a much larger cross-section in that sense.
No. Okay, let me say the same, the following. We did the same experiment in infrared, and it does not work on this scale. So the improvement is not that big. But if you go from a 10 nanometer tip to a 100 nanometer tip, you see an improvement. The point is that there seems to be some scaling with the wavelengths, and that is related with the extension of the dipole. I have the feeling. The more you go in the far field, the two poles, the monopoles, the plus and minus charges that Sasha mentioned in the finite dipole, they get more separated the larger the wavelength is, right? The smaller wavelengths, they come closer to each other. And then the effective charge distribution at the apex there's a different distribution depending on the wavelengths. And I think it's related to this. So the more you go to the terahertz, the better the blunt tips are. The more you go to the visible, there's a kind of a saturation effect when it's better. But we clearly know that using a 10 nanometer tip is definitely worse than using a 100 nanometer tip in the infrared. If you go from 100 to 200 nanometer, we didn't see big improvement. But here we see it, and I'll show you on the next slide. So, I mean, this is really a dramatic improvement. And the tip otherwise is the same. It's the same length, right? That's important. Okay, so that's a little bit more quantitative. So what we did here is an experiment. We scanned here across a test sample that is very specific. It's kind of a topography-free sample. That's actually from the reading head of a hard disk. This is a TM cross-section, though I remember when I was a PhD student, there were even people doing PhD theses on fabricating topography-free samples to make topography-free, artifact-free line scans and so on. So this is just to crash the hard disk and take it out. It works very nicely. So that's metal and that's dielectric, and then we scan over this, and there's no edge darkening artifact and nothing, right? And then you see this here. This is a log scale here. That's the 25 nanometer tip, and then we go all the way up to 750 nanometer here, and you see how the signal goes up and also the signal to noise goes up. There's also an interesting effect that you see here, namely on this sample here, a strong asymmetry in the line profile. I'm not sure whether I have time to talk about this. It's an interesting effect for itself. So material boundaries are not symmetrically imaged, so that means the point or line spread function in s-SNOM is not symmetric like it is in confocal microscopy. I have lots of slides on that too, but I'm not showing them. So because you see here this long tail here, right? So that means resolution becomes worse at 750 nanometer and it's better at 25, okay? Now we can look at this a little bit in more quantitative, so we analyze this, I don't explain how, but then we can take here a kind of a line width or a broadening of this material boundary, and then we define here an absolute resolution, and then we see that with increasing radius, the resolution becomes worse, of course. It goes from 50 nanometer for the 25 nanometer tip to about 150 nanometer for the 750 nanometer tip. Now, what is interesting, if you now calculate the relative resolution, namely if we take this number and relate it to the tip radius, and then we get this red curve here, then we see that the resolution for the 25 nanometer tip is 1.5 times the tip radius. But for the 750 nanometer tips is 0.2 times the tip radius. So we have pretty deep sub-tip resolution with this method here. And the reason for that is that we use the same tapping amplitude. That means we have an extremely small tapping amplitude, and that was mentioned by some speaker, I think Lars, that if you change the tapping amplitude, then the effect is similar to keeping the tapping amplitude constant and increasing the harmonic. So you get a huge contrast enhancement and also resolution enhancement. That's another topic that one could bring up. Adrian was asking me to talk about it, but I think time is not enough. The higher the harmonic, the better the spatial resolution. This is this virtual tip sharpening. And the same is true if you change the relative tapping amplitude. And here we have a really dramatically small tapping amplitude. So the relative tapping amplitude is, I don't know, 50 divided by 750, right? It's really small. And because of that, we get huge contrast enhancement and enhancement of resolution. And so here, that's now a numerical simulation where that's fully numerically now. What we do is here, we consider here illumination, everything properly. Then we calculate numerically the charge distribution, and we calculate here this near-field dipole that I introduced yesterday. And then we calculate the polarizability or the induced dipole moment, right, for the tip being above gold and being above this dielectric here. And then we see that the dipole moment or the polarizability of the tip increases with the tip radius, okay? And this is the absolute opposite of the field enhancement that we calculate when the tip is above the sample. So you see this red spot, that's where we evaluate the field enhancement. So the field enhancement goes up, and of course it depends on the substrate and on the distance. So the closer we bring the tip, the more field enhancement we get. And this is F, this is 10 to the power of 3, so we have 14,000. Field enhancement is 14,000, it's gigantic for a very sharp tip at a very close distance. And yeah, if we increase the radius, the field enhancement goes down. But the effective dipole strength goes up. And this is related to the fact that I tried to, this is also taken with care, that's a visualization of a verbal explanation that we give in the paper. Don't take it too serious, that's a rough estimate. So what you assume is going on here is that we have here a field enhancement, but we also have a probing area, or probing volume. And this near-field dipole, right, somehow scales with the field enhancement squared. But that somehow empirically we found, it's not completely true, it scales with 1 over r to the power of 2, roughly. This is not really correct, right? This exponent is to be explored. It may depend on many things. So anyway, so the field enhancement scales inversely to the radius, okay? Then however, then we say this dipole that we induce here depends on the interaction volume. And the volume is somehow scaled with r to the power of 3. So now if I make the simple comparison, then I have to the volume, to the increased interaction volume that I have with the larger tip, I get here this r to the power of 3 law. Field enhancement, I get for a larger tip radius, I get less field enhancement, but the scaling is different. And altogether, the strength of this near-field induced dipole scales with r. But again, this is super rough. This is not real science, what I'm showing you. This is just based on this numerical simulation where we see that. That's correct, that's accurate, that's fully electrodynamic calculation, and that is kind of an interpretation. And now that was, I don't know, somebody asked this question. It depends on what we are looking at. So far, we looked at something that is, yeah, a sample that is, let's say, bigger than the tip. Now the big question is, and I cannot give you an answer, you can think about that, maybe for next meeting in some conference, somebody could explore this. Now let's assume we have a single molecule or something that is really small. What is better than the sharp or the blunt tip? And here probably it would be better to use a sharp tip such that we focus and concentrate all the light onto this tiny little object here. That's an assumption. Sharp tips might be better, but this needs to be studied. And well, somebody maybe is interested in doing this. Maybe we're doing it by ourselves at some point. So that's the thing. That's the story regarding blunt and sharp tips. So if you have, let's say, larger areas, and you know that you have a piece of material that is rather large compared to a tip, then choose a tip site that is large. You will get more signal, but be careful because that could also strongly depend on the wavelength range that you use. So terahertz, the terahertz, this is fantastic, and it's amazing. You get orders of magnitude more signal. So that's one thing. Okay, I think that was it. Yeah, that were the 3 examples. I could stop here. I can also continue. It depends on you. If you want to have a beer, then we can stop here. Maybe I let decide the chairman. Yeah. He looks like he wants to go for a beer.
No, I want to check last round of questions before questions on this part.
Yeah.
Yes. So. I would have a question about the tip radius. So I also did some tests with the same tips, but we measure in like mid-infrared, so like 5 micron, for example, and with the 250 nanometer tips, the same ones and with something like 50 nanometers. And the problem that I consistently has was that actually I had much lower signal to noise, and spectra looked much uglier with the blunt tips.
Yes.
So is this something that maybe we expect? I was also using like 80 nanometer tapping amplitude, for example.
As I said, I don't know. We made these experiments. I think Ivan did that on. We once looked for this hyperspectral imaging paper that was cited here, where we wanted to increase the signal, and then we used these tips here for looking at bacteria, and the signal to noise level was indeed not better compared to a normal tip. But again, I mean, the nano FTR tips, they are blunter than standard tips, and that's why they are better and give more signal. That is my assumption also. There's no clear study on this. And what we did on the other, I don't have slides here, but what we did is we used particularly sharp tips. So we made tips with focused ion beam as sharp as 3 nanometer, and we achieved 5 nanometer resolution with these tips. And we really could verify 5 nanometer resolution, but we needed to average over, I don't know, 50 line scans over the same sample area, because in a single line scan, we didn't see anything apart of noise, because if reducing the tip radius dramatically reduces the signal to noise. If you go from a standard 25 nanometer tip to a, as I said, 3 nanometer tip. So it's the same effect, just going the other direction. As that in the infrared, I would say up to 100 nanometers improvement, and then whatever need to be checked. And if you go in the other direction, you constantly and continuously degrade your signal to noise while the resolution goes up. And this is like in many microscopies. No? It's also known from TEM. If you, always higher resolution often comes along with the reduction of signal to noise, and the same is true here. But there's a lot of stuff that is unexplored simply. Yeah.
Thank you.
But, yeah.
Any other question? No? Should we end here? Okay. Let's say thank you to Reinhard.